and welcome to week 2 of Introduction to Earth Science. So, in week 2, we will be looking at our solar system, so specifically the bodies that are orbiting the same star as we are. This is chapter 22 in your textbook. So, our solar system is not actually the typical solar system. Some solar systems are smaller, that they have fewer planets, some are larger, some have more than one star, some will behave basically differently. Our solar system has these parts. As all solar systems must have, we have a star. We call ours the sun. It's what everything orbits about. So the sun is producing the energy that is used by the planets, and it's also holding the planets and the other bodies in orbit with its gravity. Closest to the sun, we have our terrestrial planets. These are the inner planets. They're also called the rocky planets. So we have Mercury, Venus, Earth, and Mars. These planets tend to be smaller, and again, they're much closer to the sun. Outside the inner planets, separating the inner planets from the outer planets, is the asteroid belt. This is a area of debris, basically, so we can have some very large bodies in there. Not quite the size of planets, but still very large. We can have some small bodies, and they're being held in place by the gravity of the sun. So this is leftover debris from early in the formation of the solar system that has been organized into this fairly stable orbiting belt. Outside the asteroid belt, and by the way, asteroids tend to come from the asteroid belt, which is why they're called asteroids. Outside the asteroid belt, we have what are called the Jovian planets. Jovian refers to Jupiter-like, whereas terrestrial refers to Earth-like. So the Jovian planets are the outer planets. They're also known as gas giants. So we have Jupiter, we have Saturn, Uranus, and Neptune. Then beyond the Jovian planets, we have what's called the Kuiper Belt. The Kuiper Belt is where many of our comets live. There are other objects that live in the Kuiper Belt. These are going to be very cold. It's very cold out here. It's far away from the sun. So some of these objects will pass near Earth orbit at various times. But again, it's leftover material, much like the asteroid belt. And then further out, that's not on either of these images, is the Oort cloud. The Oort cloud is, instead of being a belt that follows an orbit similar to a single body, the Oort cloud is a spherical, not actually spherical, but a 3D enclosure, basically, that's the furthest part of our solar system. Many of our objects that cross at unusual orbital trajectories will come from the Oort cloud because they are coming from those odd angles, that they're coming from anywhere within this cloud shape instead of a fairly small area for a belt like what we have for the Kuiper Belt. I mentioned nebular theory very briefly last week, so with a little bit more detail, nebular theory basically explains the formation of our solar system and most solar systems. So the idea is that you start off with what's known as a solar nebula. So this is going to be a rotating cloud of interstellar gas and dust. This is the building blocks of the solar system. So it's an expansive gas cloud. It's primarily hydrogen and helium. There's a little bit of other gases in there and tiny dust grains. This cloud will eventually collapse, and it will have gravitational energy converting to energy of motion and thermal energy, which will make it start to spin and flatten out into a disk. The gas and... Apologies, Copper heard something. So the gas will condense down and flatten out into a disk and start spinning. Sorry, Copper just came back in and is looking all innocent. I'm watching you, dog. So the gas will condense down into a disk and start to spin. Much of the material will migrate to the center of the disk with centrifugal force and begin to collect into the center. That will form into what's known as a protosun, proto meaning before or first. This disk will start to spin faster and faster and faster, flattening more out into a disk. Material will collect and start to cool into clumps of ice and rock, and these clumps will start to have their own minor gravitational field and start to pull other material in. When you pull this material together, you will have collisions. Those collisions will increase the size and therefore reduce the numbers of clumps. So you go from 2 clumps to 1 clump. Eventually, these will grow enough that we have a few number of them that are collecting all the other material. These clumps are the planetesimals, so they are the early core of the planet. The bigger these cores are, the bigger these planetesimals are, the more gravity they have, so the faster they will grow. They can pull more material in. So as these clumps grow large enough to have their own gravitational fields, they're going to be pulling in more and more material and growing. Eventually, the majority of the dust and debris will get pulled into either an actual body or become organized into one of the belts, and we won't have massive amounts of debris floating around, and we will have the organized solar system that we see today. The composition of the bodies is going to vary with distance to the protosun. So closer to the protosun, the inner planetesimals tend to be rocky, whereas the outer planetesimals tend to be formed of gas and large amounts of ice. Early on in the formation of our solar system, we had a thing known as the Age of Bombardment. So this was when we had lots of material floating around. This was when we were forming those planetesimals and they were having many collisions to make them grow faster. Gravity will pull material into objects. That material that's being pulled into the object will, 1, increase the size of the object, and 2, bring new elements into the bodies, into the objects. So typically when this happens, we form what's known as a crater. You have a collision, and we can actually use craters to determine the age of objects by counting them. It's called crater counting. We do have to make an assumption though. So the assumption is that we have all the craters. If something has happened that would resurface the body, so we erase some of those craters, we're not going to have an accurate estimate of the age. We would then be giving an estimate of the time of that resurfacing. So crater counting doesn't work on the Earth because our surface is constantly being rejuvenated and altered. It does work very well on other bodies that don't have anything that's erasing the craters. So a crater is basically an impact scar. So the crater itself is the depression. That's what we refer to as the crater. The crater has other parts to it. So there is a rim, which is the edge of the crater that's elevated. Ejecta is the material that comes out of the crater and tends to form a blanket around the sides of the crater where it falls. So we call that the ejecta blanket. And oftentimes we will actually have a bit of uplift in the center part of the crater that's due to what's known as rebound. So basically you have massive force coming in when you have this impact, and we're pushing down the material at the time of impact. But then once typically the impactor is destroyed during this massive energy event, so since there's no longer anything pushing down on the ground surface, it will start to lift back up, and so it will actually form a small peak in the center, which is called the central peak. Whether or not a body has an atmosphere is going to depend on the temperature of the body and the size of the body. The size is important because it's going to determine the amount of gravity the body has. So large, cold bodies have large amounts of gravity, and they tend to have very thick atmospheres. Small, hot bodies don't have a lot of gravity, and so they tend not to have a lot of atmosphere. Also, the hotter they are, meaning the closer to the sun they are, the more the atmosphere gets burned off. So bodies like Mercury that are very hot and small will not have an atmosphere. Venus is large enough that it is able to have, and actually it has a very thick atmosphere. Mars has a fairly thin atmosphere but does have an atmosphere. There are a few moons, Titan and Triton particularly, that do have atmospheres. But typically moons aren't large enough to have atmospheres. So this graph, we are seeing that with the increased amount of temperature, we tend to not have significant atmospheres unless there's significant gravity, or sufficient gravity rather. These colder bodies that have high gravities tend to have, fairly strong atmospheres. All planetary bodies are layered. So we build our planets as not build them as layers, but the planets would have undergone a thing called chemical differentiation, where basically we have a segregation of different elements to different parts of the planet. Also, we had these material coming in at the surface, and so we end up having layers of the different planets. And the terrestrial planets tend to look very similar to each other. The Jovian planets tend to look very similar to each other. So the terrestrial planets, those are the Earth-like planets, they have a metallic core, which is iron and nickel. It's normally fairly good sized. The one that on the terrestrial planets that doesn't have a significant size for the core would be the Earth's moon, has a very small core. Outside the core, we have a rocky mantle. This tends to be the largest proportion of the planet, except for Mercury. So Mercury has a very large core and less significant mantle. Outside the mantle, we have a rocky crust. So this is a very thin layer, except in the case of Mercury has a thicker crust and the moon has a thicker crust. But for the larger planets, Venus and Earth in particular, they have a very thin rocky crust. On all of these bodies, the crust is the thinnest layer. So this is what we see at the surface. And then for the larger bodies, we do see an atmosphere. It varies in strength, and that would be the gas layer surrounding the planet, which is not demonstrated on this figure. The Jovian planets, the Jupiter-like planets, also have a metallic core. So it's typically rocky iron. It is not as large or it's a smaller component compared to the volume of the planet than what you see with the terrestrial planets. Then these planets have liquid layers outside the core. So for Saturn and Jupiter, they are similar to each other. They both have a layer of liquid metallic hydrogen with a layer of liquid molecular hydrogen outside that. So they have liquid hydrogen in the interior of the planet. Again, this is only possible because it's extremely cold in this part of the solar system. Remember, hydrogen is typically a gas. For Uranus and Neptune, which are very similar, it's ices, so liquid, or it's not liquid, it's a solid here. It is water and methane, but not the type of water that we would see on this planet. Then there's an atmosphere. It is typically hydrogen and helium. That's the gray layer on here. These are very thick atmospheres. So the atmospheres in the inner planets are much thinner. These are very thick atmospheres. Remember, these are cold, large bodies. So these are the gas giants, are what they're called. And they're called gas giants because they do have these thick layers of gas in them. And then the outer layer is a visible cloud layer. So for Jupiter and Saturn, they're in the yellows and oranges. The great red spot on Jupiter is actually a very long-lived storm that does move very slowly, but it moves. For Uranus and Neptune, they're very blue in their coloration, but again, those are also clouds. So now in the actual classroom, I'm going to have a flipped classroom where you will have a chance to, you will be assigned, or rather draw, one of the bodies in our solar system, and then you and your table mate will get a chance to discuss it for 15 to 20 minutes, reading about it in your textbook and discussing it. And then each table will present get 8 to 10 minutes to present the information that they have learned. I do ask that you please do not just use my summary slides at the end of this presentation to actually look into your textbook. But I am going to discuss these things a little bit in this lecture for people that miss class. So I'm going to start off with the moon. The moon is the only satellite, also known as a moon, of Earth. We call it the moon. It formed after a Mars-sized impactor struck the early Earth about 4.5 billion years ago. It's very large for an inner system satellite. Typically, if there are satellites to inner planets, they are small. This is a very large satellite. Again, it's because of this massive impact that ejected a large amount of material. Sorry about that. The period of rotation of the moon is equal to the period of the revolution. So that means that the same side always faces the Earth. So all crewed missions to the moon occurred on the near side of the moon. It has a lower density and size than Earth, so it has a lower gravity. So that's where when you see images of people walking on the moon, they bounce because there's less pull towards the body. The surface is split into the Maria or Mare, which is from the Latin for sea, and the highlands. So the Mare, or again Latin for sea, are these volcanic outpouring of volcanic material. They are younger than the rest of the moon's surface. The highlands record the early bombardment. So if we look at the Mare, you don't see as many craters on the Mare typically, whereas on the highlands it's highly cratered. So the Mare overwrote, it resurfaced parts of the moon. The moon would have been molten in the beginning like Earth, and it underwent differentiation during cooling, which formed its layers. The surface is covered in regolith. There is no water on the surface of the moon. And so all of the erosion is wind erosion and also impacts of micrometeorites. So that's why we do still see footprints from the Apollo missions. There's nothing to really erase them. And so weathering occurs very, very slowly on the moon's surface. And I believe that's all I have on my notes for the moon. Mercury is the closest planet to the sun. It is named after the Roman god Roman messenger god, and also the trickster god, or he was kind of a trickster god, and the god of thieves. The Greek version of Mercury is Hermes. It is the smallest planet. It does not have any satellites, so it has no moons. It has an 88-day orbit. One Mercury day is 176 Earth days, or 58 days, which can be confusing. So it takes 58 days to rotate for an outside observer, but it's 176 days for someone on the planet for the planet to go through one rotation. So inner planets tend to have very short years. The orbit, the 88-day orbit, is the year, but they have very long days. So it absorbs most solar radiation that hits it. Only about 6% is reflected. There's very little atmosphere. So there's very little to interfere with the incoming radiation. It does have a magnetic field. It's fairly weak. So the molten core does convect. It has similar features to the moon. We see a lot of impact craters and some volcanic flows. There is ice in polar craters, has been discovered. Venus is the second planet from the sun. It has no satellites. It's sometimes called our twin or our sister. It observes retrograde motion, so it appears to go backwards. One Venus day is 243 Earth days. It takes a long time for it to rotate. And I did not write down the length of the year for Venus. So the Venus year is 225 Earth days. Sorry that I did not write that down. So It has a very dense atmosphere that's mostly carbon dioxide, CO2. So it has a very strong greenhouse gas effect. We're going to be learning about greenhouse gases um, later on in the term. But it basically makes it very hot on the surface of Venus, aside from the fact that it's fairly close to the sun. Um, so it is, temperature is greater than 450 degrees during both day and night. There's not really a difference in temperature. There's not really a magnetic field, so the core is not convecting. The surface is hidden by very thick cloud layers. And there's incredible atmospheric pressure, about 90 times that of Earth, so it's very hard to get any data from the surface because any materials that are sent to the surface will be impacted by the gases of the atmosphere and then also this incredible pressure. There are fewer impact craters than Mercury and Mars, so there was resurfacing by volcanism. We can see these lava flows from these volcanoes. The Mons are volcanoes. The volcanic features are larger on Venus because the temperature of the surface allows the lava to flow for much longer than on other planets because it remains molten for a significant amount of time. All right. Mars. So Mars has 2 satellites. It is the red planet. It is further from the sun than Earth is. It is the most studied non-Earth planet. We see visible impact craters as well as evidence of flowing water. Currently, we only have wind erosion. There's no actively flowing water on the surface. The Martian highlands are similar in age to the lunar highlands, but then there are smooth plains of lava. Mars is home to the largest volcano in the solar system, Olympus Mons. There are no plate tectonics currently active on Mars, so that means that plumes will stay in position for they just stay put, they don't move. The plumes don't move on Earth either, but basically because there's no tectonics, the surface above the plume is always the same surface above the plume. You don't have any plates moving away from the center of volcanism. Ice has been found by different landers. We see a lot of evidence of past water. So we see water erosion features, we see water precipitation minerals, possible saltwater streaks. We do see, evidence of ice. So Mars at one point had water flowing on the surface. Mars has it takes do I not have it on? Okay, here we go. Mars has a orbital period, so its year is 687 Earth days, and it is period of rotation, so that's how much time it takes to rotate. So the Mars day is 24 hours, 37 minutes, 23 seconds. So their days are its days are slightly longer than our days. Jupiter. So Jupiter, I'm sorry. I meant to talk about the mythology on all these. Venus is named for the Roman god of beauty and love. The Greek version would be Aphrodite. Mars is named for the Roman god of war. The Greek version would be Ares. I'm a mythology nut. Jupiter is named for the king of the gods, the Roman king of the gods, which is also he's also the god of lightning. So Jupiter, his Greek equivalent would be Zeus. A fun fact: all of much of mythology problems are due to Jupiter/Zeus having various affairs. All of the moons of Jupiter are named after his various lovers. And Jupiter basically was not very discriminative in lovers. There's a large variety of them. So Jupiter has 67 satellites that again are all named after various lovers of Jupiter. Not notably his wife. Juno would have been Jupiter's wife. Jupiter's the largest planet in our solar system, but not the largest object. It is a gas giant with rings. The color is due to reflection from cloud layers. And the massive gravity of Jupiter is actually causing it to shrink. So this contraction causes heating, which drives atmospheric circulation and winds. So the great red spot, which we see here, is actually a storm that's been continuing for hundreds of years. It has the strongest magnetic field in the solar system, which is generated by its metallic hydrogen layer. Its two largest moons are about the size of Mercury. The next two are about the size of the Earth's moon. So it has some very large satellites. Some of the moons are icy satellites, so they're made up almost entirely of ice. Europa is famously one of these. The rings were discovered by Voyager the first. They are very fine particles, similar in size to smoke. It's very difficult to see them. We typically don't see them. So Jupiter has an orbital period of 12 years. So it takes 12 years for Jupiter to make it around the sun. But the Jupiter day is only 9 hours and 56 minutes long. Saturn is sorry, I just wanted to double check my mythology. So Saturn is the Roman equivalent of Kronos, who was the one of the Titans. So they were the gods before the pantheon of gods, and so all of the rest of the gods that are more commonly known are the children of Saturn/Kronos, who is the child of Gaia and Uranus, who were the absolute first. So Saturn is like the second set, and then the rest of them. Saturn has a orbital period of 30 years, so it takes 30 years for Saturn to make it around the sun, and it has a day of 10 hours and 30 minutes. Saturn's called the elegant planet because it has these very prominent rings. It has a very dynamic atmosphere with rotating storms, and that's what we're seeing in the gas clouds, the colors that we see. It emits twice as much energy as it receives from the sun, so that means it has to have some sort of an internal heat source. It has 62 satellites, but only 53 are named. Its largest moon, Titan, is larger than Mercury. Enceladus has cryovolcanism, which is ice volcanoes, and that's the source of material in the E-ring. So the rings are named with different letters. Not all of the rings are visible to the naked eye. The ring system is a rotating disk of varying density and brightness. Each ring is composed of individual particles. They just appear solid. And the gravity of nearby moons actually shepherd the ring particles. So we see gaps in, several gaps in the rings, which helps distinguish the different rings, and those gaps are due to the moons. Uranus and Neptune, or Uranus and Neptune. So Uranus is, again, the husband of Gaia, who their children were the Titans, who then in turn birthed the regular pantheon of gods. Neptune is the Roman god of the sea, so the Greek equivalent would have been Poseidon. These are very similar to each other in size, color, rotation, core, mantle. So again, they're kind of considered twins. They are different in their orbital time and the tilt of the axis. So very notably, Uranus is knocked sideways. It rotates, about 90 degrees to the rest of the planets in the system. So it was probably knocked sideways during impact. Storms are present. They're very similar to Jupiter. It does have rings, but they're not easily visible, and it has 27 satellites. So Uranus has a orbital period of 84 years. So it takes 84 years for it to make it around the sun, and its day is 17 hours and 14 minutes long. Neptune has 14 satellites. It's the windiest planet. It has large dark spots, similar to Jupiter, but much shorter lived. Triton is its largest moon and exhibits cryovolcanism, so again, ice eruptions. It has 5 named rings, which are mostly composed of dust. And Neptune takes 165 years to orbit the sun, so Neptune is very far out, and its day is 16 hours and 7 minutes long. Asteroids and comets. So asteroids are small bodies that are left over from the formation of the solar system. So they are about 4.6 billion years old. Most asteroids come from the asteroid belt, which is between Mars and Jupiter. There are about 1,300 Earth-crossing asteroids, which means that they, pass through a similar orbit to the Earth. The large asteroids tend to be spherical because they have enough gravity to be approximately spheres. Smaller asteroids tend to be irregular in shape. Comets, on the other hand, are also known as dirty snowballs. Comets have to have ice and frozen gas in them, in addition to other material left over from the solar nebula. So comets leave that tail because of the ice. Comets will come from the Kuiper belt or the Oort cloud. You can tell the ones coming from the Oort cloud because they have very irregular orbits. A comet will have a comma, which is the head, and a tail. The tail doesn't show up until it's heated by the sun. So as the comet comes in closer to the sun starts to heat up that ice and it blows it past. So it will have a gas tail that is straight and it's pushed away from the sun by solar wind. And then there will be a dust tail, which is curved and pushed away from the sun by radiation pressure. So as we get closer to the sun, we actually will see these 2 distinct tails. So you have the gas tail is being pushed by solar winds, whereas the dust tail is curved away and pushed by radiation pressure. So again, the ones that are more unusual orbits that aren't in the elliptical plane will typically be coming from the Oort cloud. And you don't see that tail until it gets very close in that it's being heated by the sun. All right, meteors, meteoroids, and meteorites. And for some reason, I have the hardest time trying to write these words. So one of the best ways that we see evidence of large past meteorites is craters. We do have some significant craters on our planet. Not as many as on other planets. Here we have meteor crater. We see a cross section of what the materials look like, and we can actually see this ejecta blanket and how it's been eroded away. This is an example of a very large meteorite. So shooting star is an inaccurate term, no matter what you're talking about. So sometimes people call asteroids shooting stars, sometimes they call meteors shooting stars, or comets shooting stars. None of them are stars, for one thing. So when we see something light up through the sky, that could be a comet moving past. It could be a meteor in our atmosphere that's being heated up by our atmosphere. It's not going to be an actual shooting star, though. It's not a star. We call a meteoroid is when the object is in space. Once it enters the atmosphere, we call it a meteor. Sometimes they blow up in the atmosphere, and those are airbursts. And if it hits surface, we call that a meteorite. Most meteorites now are found in Antarctica, and I'll explain that in a second. There are different types of meteorites. We have iron meteorites, which are typically iron and nickel. We have stony or chondrites meteorites, which are silicates. They record basically a good snapshot of the the chemistry of the bulk chemistry of the solar system. We also have stony iron meteorites, which are a combination of the two. Some of the most impressive meteorites are primarily iron and nickel, and then they have these beautiful olivine crystals that are bright green in the middle of the metal. So those would be stony iron. And then we can have a special type of meteorite called carbonaceous chondrites. So it's a stony that has organics included in it. Meteors or meteoroids are thought to be the same material as the bulk universe, or at least the terrestrial planets. So they are very useful for understanding our solar system and universe. So where do impacts occur? They can actually happen anywhere, but they tend to happen in certain locations. So we do just get a lot of impacts at the poles, but then there are certain places where it's easier to find them. So you have a high number of objects found in Antarctica. This pie chart is showing us the percentage of meteorites found, large percentage found in Antarctica. The next largest are in the Sahara Desert, and all the other major contributions are other types of deserts. So deserts, whether it's a polar desert or a non-polar desert, are great places to find meteorites because there's not a lot of rock sources available. So if there's not a lot of rock sources available and you see a rock sitting on the ground, where did it come from? The other thing is deserts tend to be light colored, so it's easy to see rocks. You're able to identify them. Antarctica in particular has the unique feature of having these thick layers of ice. So when the rocks fall, they get trapped up in the ice layers and they get buried in the ice. The ice is constantly moving, and so you end up having all of the material that's been trapped in the ice that fell on the ice will collect in fields, and meteorite fields basically. So every year there are people that, it's an honor to be chosen to be on the team, but they go scour the known meteorite fields and just collect new meteorites. So this chart here is showing us the numbers of meteorites, and when we see this, found per year, we see this drastic uptick when they started collecting meteorites in Antarctica. You can actually buy meteorites on eBay. People that find them will then break them up and sell them. I actually have a couple samples from a meteorite that fell in Licking, Missouri, mainly because my family lived very close to Licking, Missouri. So you do have falls happening everywhere. And finally, the dwarf planets. So the most famous dwarf planet would be Pluto. Pluto is the Roman god of the underworld. The equivalent in Greek would be Hades. A fun fact, because I just want to share this because I'm a dog person. Dwarfs are it has to do with a miniaturization of parts of the body. That's where the term dwarfism comes from. So in the dog world, basset hounds, dachshunds, and corgis are all called dwarfs because they have a specialized type of dwarfism that miniaturizes only their legs. So it's just the legs that get miniaturized. In a lot of cases, they do not miniaturize very straight, but the rest of the dog is standard size. So they're not a miniature dog, they're a dwarf dog. So actual dwarf planets, Pluto was found when a planet was needed to explain irregularities in the orbit of Uranus, but it turns out Pluto is too small and far away to actually explain the irregularities, but it was a body that was discovered. Other large Kuiper Belt objects meant that Pluto actually lost its status as the 9th planet, because if Pluto is a planet, these other bodies would also need to be planets. So in 2006, the term dwarf planets was decided to be the new object class for bodies that orbit the sun and are essentially spherical due to their own gravity, but they're not large enough to sweep their orbits clear of debris. So examples are obviously Pluto, Makemake, Eris, Ceres. There's several other large Kuiper Belt objects. There are some moons that could also be considered dwarf planets, but they are orbiting another body. They're not orbiting the sun itself, so they're not technically dwarf planets. And I believe that is all. I do have my notes listed on here as well, but these are the things I was just reading out. So I will see you in class this week.